welcome back. I hope you're ready to do an investigation into a bouncing ball, and hopefully this will make it sort of make sense to you, okay? So, what we're going to do is we're going to investigate the physics of a bouncing ball, and I'm going to include things like momentum, I'm going to include impulse, I'm going to include kinetic energy, because it's important for you to see a whole picture, okay, and not just isolated bits of physics, because everything works together. So, here we go. I have a 150-gram ball, so it's not very big, dropped from a height of 1.55 meters. Now, I know you can't see from where you are sitting from the screen, but that's how tall I am, so I know it's dropped from about this height, okay, just as a reference. It hits the floor, and is in contact with the floor. That should say floor, not fall. Anyway, for 0.2 seconds, and rebounds, so it hits the floor, then bounces back up at 5 meters per second. Now it's dropped, so my very first velocity is 0. The ball then hits the floor a second time, and now rebounds at 4 meters per second after being in contact for 0.2 seconds again, okay? Now this may not be complete. I've tried to make these values as accurate as possible, but there may be some little errors. It's all right. So what we need to do is I need to know the velocity when it hits the floor for the first time. So I want to draw some graphs. So I know my initial velocity was 0. I want to know what its final velocity is. I'm going to take down as positive because it was dropped, which means my acceleration now is 9.8 meters per second squared. I don't know delta t, but I do know delta y, because we said it was 1.55 meters, okay? I want the velocity when it hits the ground for the first time. Going back to our equations of motion, the best equation is delta y, vi delta t. No, I can't use that one. I'm lying to you because I don't actually know time. So that's not a good one. The one I'm trying to get to is Vf squared equals Vi squared plus 2a delta y, where Vi is 0. This is 2 times 9.8 times 1.55. Absolutely need my calculator. So we've got, let's just get rid of that. The 0 we don't need to worry about. So we have 2 times 9.8 times 1.55. That gives me 30.38, but I'm going to need to square it. So now I'm going to take the square root of that answer. And, oops, we get 5.51. That's what I'm going to use. So my final velocity is 5.51 meters per second down. What I also need to know is the time taken. At this point, I have several equations I can use. I'm just going to use the one that, quite frankly, is the easiest, which is Vf equals Vi plus a delta t. Of course, you could use delta y equals Vi delta t plus a half a delta t squared, the other one. But then there's a square on the t, and let's just make maths easier. So 5.51, that's 0, 9.8. To get time on its own, I'm going to divide 5.51 by 9.8, and I get 0.46. So, seconds. So what I've worked out now is I know initial velocity, I know the velocity it hits the ground with, and I know how long it took to get there. So that's important pieces of information that we need to keep. Now, I want the maximum height after the first bounce. They told you, if we go right back to the original one, it rebounds at 5. So the initial velocity now is minus 5. Why am I saying minus? Because I took down as positive, okay? I can't change it because I'm trying to find something else. So now this is minus 5, okay? Gets to its maximum height, which is VF, which will be 0. I know my acceleration is 9,8. I don't know the time it takes to get to that height, but I want delta y. So looking at the information, again, I'm going to go VF squared equals VI squared plus 2A delta y. VF is 0. VI is minus 5 plus 2 times 9, whoopsie, I keep doing that, 9,8 delta y. I know minus 5 squared is 25, so I'm going to take it over. It's going to be minus 25 equal to 19,6 delta y. We definitely need our calculators. So we've got minus 25 divided by 19.6. And we get minus 1,28. I'm going to round off to 2 decimal places. I'm happy with that being a minus because I said down is positive. It's now moved up. So the maximum height is 1,28 meters. Okay? We want the velocity when it hits the floor for the second time. So that's the next thing. Oh, that's the third time. So let's just go here. Velocity when it hits the floor for the second time. Well, this one's not a calculation. Okay? It left the floor at 5. It's going to hit the floor at 5. So that velocity is going to be 5. Straightforward? Now we want the time taken to hit the floor for the second time. So we're just going to do it over here quickly, where we go VF equals VI plus A delta T. My VF is 5. My VI was minus 5. A is 9,8. This becomes 10. And so delta T is going to be 10 divided by 9.8. And we get 1,02 seconds. So that's the time it takes to go from the floor, get to the top, get back down. So that's the second time it hits the ground, the first bounce. Then we get to, oh, it's over this side now. Okay, so now we get here, and now they want the maximum height after the second bounce. If we go back to what I gave you, for the initial velocity of the second bounce was 4. Okay, we know VF is 0. We know A, and actually that's minus 4 because it's going up. A is 9,8. And we want delta T. Eventually, we want delta Y. So we've done this more than once. And we go VF squared, VI squared plus 2. Oops, don't forget the square. Delta Y, that's 0. And this is minus 4 squared plus 2 times 9,8 delta Y. 4 squared is 16. Okay, so minus 16 divided by, oops, 19.6. And now it's only minus 0.82, so it's significantly lower. And I'm okay with that. All right. Velocity when it hits the floor for the third time. It left the floor at 4. It's going to hit the floor at 4. So Vf is a positive 4 meters per second. Time taken to hit the floor for the third time. So Vf equals Vi plus A delta T. That's 4. That's minus 4. 9.8 delta T. Calculator. Okay. That's going to be 8 divided by 9.8. Delta, oopsie. It's going all over the place. It's getting very excited. So delta T, 0.81 seconds. Why did we do all of this? So that we could put that information together on a graph, okay? So, velocity time graph. And we're going to do this very quickly. Was dropped. Initial velocity was 0. Bounced, hit the floor at, we worked this out, give me a second, at 5.51. Bounced, left the floor at 5, oops, got to 5, bounced, got to 4, and then it hit the floor again. So, this is 5. This value here is minus 5. This, not minus 5, it's plus 5. That value is minus 4. This value is plus 4. And then, of course, it hit the ground again. So that's where it hits the ground. All getting very messy. But what I want you to see are these lines. Okay? And we could put times in, but we're running out of time. And we were putting all the values we learned. Okay? My velocity time graph now changes. So it started at 0. We realized what its maximum height was. It bounced, and it bounced again. So this height was the first height, which was 1.55 meters. Don't forget this is delta y, and this is time. This height was the second height we calculated, which was 1.28, and this one here was 0.81. Not even vaguely to scale, but that's okay. We'll live with it, okay? The acceleration time graph, here things are a little different because I know when it's in the air, it's at 9.8 meters per second. Every time it's in the air. But then there's moments where the acceleration changes. And I don't want to get too caught up with that because that's the time it spends on the floor, okay? So for all intents and purposes for us, it's a constant. We are going to ignore, in reality, we are going to ignore the time it ends on the floor. I put the time in because we want to look at what happens with momentum and impulse. Okay, so with that information I've got, I can absolutely work out how its momentum changed, what force it experienced, and what its impulse was, because I know the time in contact with the floor. Okay, so that makes life a little bit easier for us. And those are the things we would be able to work out, but we're not going to worry about them. So, lots of calculations, but we got to see what the graphs would look like. So now, we're going to take a short break to catch our breaths, and I'll see you in a couple of minutes.